Hi, welcome back. So we're going to start to shift focus now into a new algorithm that is a type of regularized regression. And regularized regression is a way of, it's a regression technique, and it's a way of preventing overfitting by reducing the model complexity. So first of all, let's remember what it means to overfit and what it means to have a complex model. So I have a data set here, and this is a one-dimensional data set. So I have one feature, and this is the target. Remember, in regression, the goal is to predict a continuous variable. So that's the target, right? So we're not dealing with classification here. Now, given these four data points, I could write, maybe like a quadratic, or not a quadratic, maybe a cubic, and I could fit that really tightly, right? And you look at that and you say, wow, that's a really good fit. Of course, I could also just fit a line. Maybe this is the best fit line. And you look at that and you say, well, which one fits better? And the one that fits this training set better is, of course, the cubic, right? But the issue with overfitting, we would, I guess before we get there, we would say that this is a high complex model, or high complexity, I guess. Okay, and this is a low complexity model. All right, now, the issue here is, and you look at the high complexity model, you say, wow, that's a great fit. But the issue is not how good do you do on the training set, it's how good do you do on predictions, on data that you have not seen before. So now I ask you this, if a new training example came in with this feature right here, right? You say, well, what would you expect that to have a target as? And this cubic predicts that target to be somewhere up here, right? And this model predicts the target to be somewhere around here. And look at the four blue points and then look at the red point and you say, well, where do you think that would occur? And it's likely that this one is going to be the better fit, the low complexity model. It's likely that it's not going to be way up here. Okay, and this concept is called overfitting, right? So we would say that this is overfitting the data. Okay, the idea is that it's learning the noise in our data set. It's fitting too tightly so that it cannot generalize to new data well, right? And this low complexity model is usually the one that we prefer. Okay, so regularized regression is going to be a way of handling this. Now, how are we going to do that? Well, this cubic can be written like this. Theta, I think we'll call it theta 3 like this. X, if the feature is x, theta 3 x cubed plus theta squared, or theta 2, excuse me, x squared, plus theta 1 x plus theta 0 is the bias term, right? This in our prediction is y. I guess this is the ith prediction, so this is xi, xi, xi. And the idea is this, so we could fit a cubic, and we really don't know. So, we could start with a cubic. We don't know that the line is the best one. And then, but notice that, or I might get some constants. So I use gradient descent, or maybe I use ordinary least squares, and I get these constants, these theta 1s, theta 0, theta 2, theta 3. And so I have this cubic. Now, if I could some way force, in a strategic way, these coefficients to get lower and lower, like the cubic term, particularly the cubic term, if I could force this to get lower, do you know what happens to a cubic when that coefficient gets smaller? Well, it becomes less like a cubic, right? It'll become like this, and then it'll eventually become like this. It becomes less like a cubic because this is getting smaller, closer to 0. That's what I mean by smaller, smaller magnitude-wise. And so it becomes more like a quadratic. And then if this thing starts to shrink, the quadratic becomes more and more like, you know, a line, because then this thing goes to 0, and then we have more and more like a line. So therefore, if we had some strategic way of shrinking these coefficients, then that is reducing the model complexity, and it's making it more like a line, right? And ultimately, we could even shrink this thing so that it's a constant, right? And then we would shrink this thing, and so that we have 0. So that represents the extreme case of the smallest model complexity. Okay, so regularized regression. Regularized regression is actually going to do a couple things for us. So first of all, and the main motivation is to reduce model complexity. I want to emphasize that. Okay, but it turns out there are some other uses for regularized regression that I'm going to explain in future videos. We can convert an ill-conditioned problem to a well-conditioned problem. Okay, again, I'll explain this in later videos. And 3, we can reduce the dimension of the problem by what's called feature selection. So, and you can kind of understand number 3. If I shrink theta 3 to exactly 0, then that's saying, okay, the feature 3 does not really matter. That it's the only other features that matter are these the bias, the first feature, and the second feature. So if I shrink these to exact 0, then I'm essentially selecting features out of a set. And we're going to look at 2 types of regularized regression: the ridge regression and the lasso regression. And the ridge regression is going to do these 2 things for us. And the lasso regression is going to do all 3 for us. You say, well, why do we even look at the ridge? The price you pay, it turns out, to be able to do all 3 of these is computational effort. I can't even write that. Computational effort. It turns out that to solve the lasso problem takes a lot more computational effort than it does to solve the ridge problem. So that's kind of the trade-off. Just like in everything in engineering, there's going to be a trade-off. All right, so in the next video, we're going to start to look at ridge regression and how that can help us avoid overfitting. So let's take a look at that.